In our last video, we talked about the basics of energy and how energy is the ability to cause change. We also talked about kinetic energy being energy in motion. Next, we're going to start talking about gravitational potential energy. Based on your previous knowledge, I would typically ask my students to tell me what they think gravitational potential energy would be. So we usually start is gravitational means it has something to do with gravity. Also, we talk about how if it says potential, potential is stored energy. So it is energy that's going to be stored based on the gravity of the object. So one thing that we're going to talk about is that not all energy is moving energy. It's not all energy that you can see. So since it's not all moving, some energy, gravitational, stored energy based on an object's height above the earth and its mass. So just like we talked about earlier, sometimes we can show it using different variables. So some people like to write it as GPE, so that it's the gravitational potential energy, or a lot of places like to use U with a lowercase g. The U symbolizes potential energy, and we'll see it again later. And then the G shows that it's the gravitational potential energy. So either one you might see, and that's totally okay depending on what textbook that you're looking at. So the equation for GPE, gravitational potential energy, is this. UG equals M times G times H. So again, this is gravitational potential energy, mass, gravitational acceleration, and height. And by height, it's going to be how much that height has changed. So let's talk about our units again. So our units are going to come back. If we're talking about energy, it's got to be in joules. Mass, again, just like always, is going to be in kilograms. The acceleration of gravity is meters per second squared. And then your height will also need to be in meters. Now, if we found it on the AP Physics sheet, it's going to look very, very similar, but just a little different. So if you found it on the AP1 equation sheet, it looks like this. So it's delta UG, which means the change in potential energy, times mass times acceleration of gravity times delta Y, or your vertical change or your displacement. Now, like we talked about earlier, if this is stored, we're talking about how much is stored extra. So if something is on the ground, then it's not above the ground. So to give it more energy, the potential for it to make a change or to do something, you have to change its height. So how much you change its height is by how much you change its energy. So for example, if I have a little ball right here and I take this ball and I move it up to that spot right there on the 10-meter platform, I have given it more energy, so I have changed its amount of gravitational potential energy by moving it up. That distance right here would go in the delta Y, or the height change category. If I needed to do it again and I wanted to take it up to the top of the 20, I'm technically gaining the same amount. Like if I went up by 50 here, I would go up an additional 50 here to get from the 10 to the 20. So in total, I would have 100 joules extra. So that's an example of how it's changing, but you don't necessarily just have 50, because for the same thing, if I had initially began, instead of this being a flat surface, if this was on top of a mountain, and then this is considered the flat spot, and I go up on some giant box on top of the mountain and then go up on another giant box on top of the mountain, I'm still way higher on the earth, but I'm only looking at how much it changes by how much I change its height. So the height of the mountain never really matters. It's how much you are changing each time. So let's come down here and look at a couple example problems. How much potential energy does Malik, mass of 60 kilograms, there's my mass, gain when he climbs a gymnasium rope up a distance of 2.5. So here's my equation. From here, I'm going to plug in the things I know. And just like we always need to remember, the acceleration of gravity on Earth is technically 9.8 meters per second squared. Now, if you are on a mountain or in a really, really deep valley or something like that, it's going to be a little off, but for the most part, it's 9.8 all over Earth in general. Which, on the AP test, if you take the AP test, you're going to round it to 10 meters per second squared, and it'll help you with a lot of your detail work, not getting lost in all the decimals and stuff like that. So, we're going to plug that in here. Our mass was 60. Gravity was 10. And our height is 2.5. And so whenever we plug those in, we get 1,500. And the unit for all energy is joules. And so if you wanted to, this is what you really need to think in your brain. This is a kilogram. This was in meters per second squared. And this was in meters. So technically, your units are doing the same thing that your numbers or your variables are doing. So you're left with a kilogram times a meter per second squared times a meter. Meter times meter makes it a kilogram times meter squared over second squared. And we learned earlier in the first video that that is the same thing as a joule. So that's where your units are coming from here. And as long as you always make sure and use the right units when you're starting your equation, then whatever you get out, they'll all match up the right way. So make sure that our units are where they're supposed to be. All right, looking at the next one. What would be the mass of a box on a 6-meter ladder that had 479 joules of potential energy? This time, instead of using the 9.8, we're going to use 9.8 instead of the 10, just so that we can work with some more decimally numbers. So start with your equation. Plug in the things that you know. This time we know our height was 6. We know that we had this many joules of potential energy. So the 479 actually has to go on the other side of the equation. We are looking for the mass, so keep your M. And gravity, we should know in our brain, we can either use 10 if you are in the AP class. If you're in a regular class, your teacher's going to want you to use 9.8. So, go ahead and multiply these two things together. You get 58.8 times your mass equals 479. I'm going to keep going. We'll come back and erase in a second. And since the 58.8 is being multiplied by the mass, we're just going to divide it on both sides, 58.8. Those go away. And the box must be 8.15 kilograms. Now, there was more to that decimal, but I rounded to 2 decimal places. So, that's how you would solve for the mass in this equation. Now we're going to redo the same thing or another problem. I'm going to erase this. I'm sorry. So we can read. One thing that I encourage you to do, if you don't have a lot of paper, get more paper. If you don't have a lot of space here, you either need to learn to write small or always use an extra scratch piece of paper where you show your steps, plugging in each line at a time so that your teacher can help you find your mistakes if you make them. And if you show them step by step, you're much less likely to make mistakes if you take it one thing at a time and try not to do it all in your head. All right, this time it asks, how high above the ground? So that means I'm looking for my height. Would a 45 kilogram kid, so that's my mass, be if they had 600 joules of potential energy? They told me it was potential. And I'm assuming because they have height and mass, that tells me it's going to be gravitational potential. We're going to look at another type of potential in just a little bit. And when we do, we'll notice how they are not always giving you the same thing. So even if they talk about potential energy, you got to know which one to use based on what they've given you. So equation first. Plug in the things you know. You know they had 600 joules of energy. Your mass was 45. Gravity is 9.8, and you're looking for your height. So again, we'll multiply those two together. 600 equals 441 times your height, and then you'll divide both sides by 441. And you're left with your height to be 1.36 meters above the ground. So that's about 4 feet-ish if you had to guess. So that being said, this is kind of an overview of how you would use gravitational potential energy and solve problems based on it. Now, I just said that we had gravitational potential energy, but we also have another type of potential energy, and that is spring and elastic energy. So the spring or the elastic potential energy is the energy that's stored in an object whenever you stretch or compress it, like a rubber band. Here's your thing. The elastic potential always depends on the distance that it's going to be stretched or compressed, and how strong that spring or rubber band or whatever is. So because of that, if you think about like a ponytail holder, if it's just chilling right there, it's not doing anything. It doesn't have any of this potential energy because it's just chilling. However, whenever you stretch it out like this, like you can stretch it like a slingshot, you put it by your friend's arm, you can pop it and it can hurt. So the more you stretch it, the more pain it can cause. And because it can change their opinion of you, it can change the amount of energy that they have. So, again, some rubber bands are really thick and strong, and some are really thin and not. So, how strong it is going to come into play. But if we're going to figure out how much it's stretched or compressed, you must know the relaxed length and then find the distance or displacement for its new position. So to find displacement, remember displacement is delta x. You're going to use final minus initial. Also, one thing to remember with this type of energy, if you stretch the rubber band out, it's going to try and oppose or give you the opposite direction of force. So if you're pulling something to the right, it will be pushing it to the left. It will try and pull you back to the left. Or like with a spring, if you push a spring down, the spring is trying to spring you back up like a pogo stick. So the spring constant is a parameter that measures the spring's resistance to be stretched or compressed. It's really like how strong it is. So let's write the equation itself for this. Whenever you're looking for it, again, potential energy is using a U. So we're going to do US for spring potential or elastic potential, and it's 1/2 kx squared. Now, a couple important things. Let's look at it. Elastic spring potential right here is our US. 1/2, K is your spring constant, and X is the displacement, which is a little different than whenever we were talking about it earlier. The only difference that you should see right here is that you have to know that this is displacement, even though you don't have the delta in front of that X. So many times you're going to have to do this on your own without really being reminded to do that final minus initial. So always make sure you're only putting in there how much it's changed. So here's your units. All right, so joules, again, is our energy unit. The spring constant is actually a Newton per meter. And so whenever you do Newton per meter, for it, you could go back and find the spring force. And the spring force is where you get that right there. And then you have your displacement is got to be in meters. But remember, again, you got to square it. Also, whenever you square it, it's going to get rid of that negative. So it doesn't matter if you're pulling it to the left or if you're pushing it down or which way you're doing it. It's just because you got to know that the spring is always going to be trying to get you to do the opposite of which way you pushed or stretched it. So let's look at a couple equations. If you look at it on the AP Physics 1 equation sheet, this is the only difference. And again, it kind of goes back to what we talked about with gravitational potential energy. It's a delta because you are only going to change its energy when you change its displacement. Your spring constant is where you're going to get how strong, like its multiplier, because if you have a strong spring and you stretch it, you should have more energy compared to a weak spring. So there's an idea where those deltas come into play to help explain some ideas behind the physics, but it's not necessarily going to change your equation a lot. So let's look at some problems now. A spring with a spring constant of 550 newtons per meter is compressed 7,800 millimeters. What is the elastic potential energy? So it tells me right here, there's my K, that's my spring constant. But I got a problem because they told me how much I'm stretching it. But you should see right here, it is not in meters. That is my delta X, but it's not in meters. So to move it, remember millimeters is 3, so 1, 2, 3. So it's 7.8 meters, which is a really big stretch because 7.8 meters is a lot. But we got this. All right, so start with our equation as always. We're trying to find the elastic potential energy, so I want to keep the US there. I'm going to do 0.5 times my spring constant, which is 550, and our displacement is 7.8. Now, please, super extra, be careful. Square that. Square it, square it, square it. And type it in your calculator, and you get 16,731 joules. So again, I said that it's got to kind of be a lot. That's a lot of energy because that's a pretty big distance that you're stretching it. Let's look at another one. A spring has a K of 88 newtons per meter. So we've already got that one. How much must this spring be compressed to store 45 joules of potential energy? So this time, they're not asking for the amount of energy, they're giving it to us. So we got to work backwards. Start with our equation. Plug in the things that you know. Then try and solve for X. So whenever you do, you can go ahead and simplify the things on the right side of the equation if you would like, or you can do them individually. I'm going to go ahead and do them together though. Half of 88 is 44. So knowing that this is really 44, I'm going to divide 44 on both sides. So 45 divided by 44 is going to be really close to 1. Because I get 1.022 and it goes on, but we're just going to round it 0.23. And then at the end, because it's being squared, you're going to have to make sure and square root it. Now right here, because it's just 1, it's not going to be a super big difference whenever I square rooted that. And I get X equals 1.01 meters. That's how much it's going to be compressed. Now, one of the things you want to think about is it said compressed. It didn't say stretched. But because you have this squared and you were square rooting, remember it could technically be a positive or a negative. Either way, whether you push it or stretch it, you're going to get that same amount of force if you are moving it the same distance or displacement. All right, let's look at the last one here. If it requires 6 joules of energy to stretch a particular spring by 2 centimeters from its equilibrium position, how much more energy is needed to stretch it an additional 4? So this is like a multi-step problem here. We got to do the first problem and find what we're missing to be able to plug it into the second problem. So think about the first spring. If this is my initial spring, I'm now stretching it by 2 centimeters. Remember, centimeters also is already in the wrong position in our brain, so we got to change it from 2 centimeters to 0.02 meters. Now let's start with our equation, just like always. Plug in the things you know. I know my displacement is 0.02, and I also know it said it took 6 joules of energy, so I'm going to put it there. Look, y'all didn't even correct me. That should have been an S. I'm so sorry. All right, so, and I still got my 0.5. So that means I must be looking for my spring constant. That's the thing I need from my first half of the problem to help me in my second half of the problem. So we're going to solve for K. Go ahead and square it, multiply these two, and resolve it. When you do the right side, you get 0.0002 times K equals 6. And whenever you divide 6 by that number, it's got to get bigger. And you get 30,000 as your answer whenever you divided that. So that is a like super extra strong spring, and that is totally okay. All right, so that's not a J. That should have been a Newton per meter. I'm so sorry. Okay, so now you're going to take that spring constant and you're going to plug it into this next one because you want to figure out how much more energy is used. So let's take the same thing, and this time we've got to think about our spring in its new position. So if it was originally like this and you're stretching it an additional 4 centimeters, now it's that 2 plus the 4. So 2 plus 4 equals 6 centimeters. And 6 centimeters is 0.06 meters. Use your equation. Again, same one. 1/2 kx squared. You've got your spring constant this time. So we're going to do 30,000 as your spring constant times your displacement squared, so 0.06 squared. And you get your elastic potential energy for this one just to be 54 joules. Now you're not quite done. That's how much it would take, but it didn't ask how much. It asked how much more. So in the very end, you've done a whole lot. You've worked a long problem. You got to finish it out. If it took 54 to do it the second time, but it really took 6 to do it the first time, you got to subtract them to get 48 joules would be the difference, or how much extra energy you needed to solve that. So you can see some of your problems are going to be pretty easy, like the first one, and the second one wasn't terrible, but you can get into some crazy stuff if you get into some of these extra ones where they may ask you to do something more than once. But you use the same processes and you can do every type of problem with these equations. You just got to take it one piece at a time. So let's do a recap. We've talked about energy. We've looked at kinetic. We've looked at energy as it was. We've looked at the 2 types of potentials, spring and elastic potential. Now, one thing that's cool about all of these is they all come together in what we call mechanical energy. And in another video, we're going to learn about how these can interchange and go together with each other to learn about how mechanical energy, if one thing goes up, the other goes down, because the law of conservation of energy says energy cannot be created or destroyed, but it can change forms. So in another video, we're going to learn about how mechanical energy can include all of those things that we've done: kinetic, gravitational, spring, elastic, and even one more we haven't talked about in work, and how they go between different forms and how you can use your equations to help find a piece of another one you think might be missing. So we'll talk about that in another video. I hope you have a great day. Thanks for watching.